Hello, everybody. We're going to re-record the last session due to a lot of technical glitches, and we're going to send this out with an email reminder. We also discussed the fact that our next workshop will be December 10th. So I'm going to do a few introductions, and then I'm going to cover outliers. And then part two by David will be how do you bin data or discretize data. So first, though, a few announcements. Number one, we have a new website that we put together. We haven't populated a lot, but I plan to share data under the file share and have content for you from time to time that we'll host here. So it's nocodedatascience.net is the URL. I want to go over two other websites. The first one is the University of California Irvine Machine Learning Repository. It has over 600 data sets. Some are medical, some are not. It tells you what kind of data is there, what kind of tasks such as classification or regression, attribute types such as categorical and numerical, the number of instances, which is rows, and attributes or features, and the year. In addition, often it'll tell you who wrote it, and if there's any publications related to it, they'll give you publications as well. The second website is brand new. It's literally like a week old. This is one of several sites that uses AI to generate synthetic data. What caught my attention, though, is they have a free tier that seems to be good forever. They say that you can generate up to 100,000 rows of data per day. So I did 3 projects that seem to work extremely well, and the data seems to be very much similar to the original data. So it uses AI to go in and study the patterns, learn it, and generate more data that you can use for machine learning or AI. And the other thing I thought that I would do is have a word of the month, which is going to be stochastic, which is a word you'll see with machine learning quite a bit. It means basically randomness. And you'll notice that in orange when you sometimes try to do a model and you get an AUC, and then you do it again the next day and the AUC is slightly different. Or a friend uses the same data, uses logistic regression, and the results are slightly different. That's a stochastic difference. That's just a certain amount of built-in randomness. Okay, let's get started on the textbook chapter, then I'll go over some orange widgets. We're going to start with handling outliers. This is a fairly common problem, and you have to deal with it similar to missing data. You have to figure out, is that an outlier you can live with? Is it an error? What is it? There's 2 general definitions. One of them is it's greater than 3 standard deviations above or below the mean. So looking at figure 2.10, here the mean is 207.23, the median is 203, standard deviation is 44. So if you multiply 44 times 3 and add it to 207, anything above that would be an outlier based on that rule. But there's another interesting rule. If you look at this box plot, first of all, the minimum's way out on the left, the maximum's way out on the right. These dark lines are the standard deviation. This big blue block is the interquartile range from the lower 25% to the upper 75%. If you subtract them, the interquartile range is 229 minus 179, or 50. If you multiply that times 1.5, that's 75. Therefore, an outlier is greater than 304 because that's 229 plus 75 rather. And conversely, if it's less than 104, it's an outlier, and that's 179 minus 75. So those are two ways to calculate it. You'll want to visualize it, and we'll show that to you here in a second. Keep in mind that decision trees, support vector machines, and k-nearest neighbor tolerate outliers, but others don't as well. You can run the model with and without outliers and see what happens. And we'll show you several ways to visualize it. But as clinicians, you need to make a decision. Is that result believable? Have you pulled any old lab tests on this patient? Is there any secondary reason for this patient to have an unusual, let's just say, lab result? So there's where the clinician can certainly be valuable, trying to make sense out of a result to see whether it's real or not real. As we see with some of the visualizations, and I'll scroll down, these are some that David posted, and I'll show you some in the orange widgets, is that you can look at several things. Like this is a scatter plot, and David has put a box over ones that don't seem to be right. They're way out. They don't seem to belong. He did a line plot. By the same token, showed some highs and lows that were out of the ordinary. A linear projection is one I don't use very often, but you can clearly see there are some blue dots here. These are not supposed to be diabetic, but they're in the diabetic range. Violin plot, the portion that's with the box around it is systolic blood pressure. They seem to be outliers. Here's a box plot in the lower left that I've already kind of showed you, that there are people that seem to be outliers. And lastly, here's distributions. And if you look over in the far left, this is waist. This is people with a tiny waist, which could be real if they're very young, could be a mistake, or they could be cachectic and sickly and have a small waist for that reason. So I'll show you the orange widgets, visualization widgets, in a second. I do want to mention that there is an outlier widget that helps you locate the widgets and get rid of them. But again, some caution, because you can overdo it. The default is called local outlier factor, which is a Python package. And they ask for the contamination, and that's the percent outliers in the data. You have to calculate that and see it's probably no more than 5%, 5 to 10%. But these are the four algorithms, if you will, to calculate outliers. I'm not going to go into each one. These are explained well on the Orange website and the help menu, but I think the default is reasonable. It works well with non-normally distributed data, and frankly, most medical data is non-normally distributed. I wanted to just demonstrate here that I looked at cholesterol before and after using the widget. In other words, here in this first diagram, 2.11, you notice the cholesterol is fairly normally distributed, but in the far left, somebody has a cholesterol down really low, and this is a total cholesterol, somewhat hard to believe, it's like 75. And then there's several people with cholesterols over 400, which is, they're definitely outliers, they're believable. So basically, I used the outlier, and that got rid of, I believe it was 15 outliers. So now it looks more normally distributed yet, and fewer outliers. And so that's the result of that. So let me bring up the widgets. This is a diabetes data set. I'll open up that basically we determined that diabetics for anybody with a hemoglobin A1C over 6.5. Less than that, you're non-diabetic. That is not perfect for a couple of reasons. We don't know if these people are on medications, for instance. They may have had a normal sugar and an abnormal hemoglobin A1C, or vice versa. So in any case, looking at the linear projection, you've really kind of already seen that. I want to point out the blues here don't really have any business being there. And you can see mousing over it, it says non-diabetic, but the glucose was 371. So something's wrong somewhere. Could be a lab error, because the other aspects look pretty normal, the BMI and whatnot. So this person may, in fact, the lab test, the glucose may be what's wrong. And what I was showing you here is you can always connect it to a data table and then look at the same information here and try to say, does that make sense? Is it real? To me, this doesn't make sense. This person doesn't seem to have the features of a diabetic. So perhaps that lab test was transcribed on the wrong chart. And here's saved data. So if you wanted just that patient alone, use the saved data widget. A box plot, we pretty well already demonstrated. Keep in mind here, I'm looking at cholesterol for all patients. When I click on by group diabetes, now you can see at the top 0 for non-diabetic and 1 for diabetes, and that the t-test suggests that there is a difference. Cholesterol in diabetics is higher than non-diabetics, which is certainly believable. And also, if you click order by relevance to subgroup, it's telling that the glucose was the most important, age was number 2. No surprise. Violin plot I already showed you. Another way to look at distribution, if you will. Most of the people systolic blood pressure fall in this middle range, but there were a few people, even though they did not have diabetes, they have systolic blood pressures over 200. That's probably real. Was that anxiety? It's hard to say. You'd want to investigate that further and see whether that's really real, particularly if they had more than one blood pressure recorded. Scatter plot, there's a valuable way to do that, and that is if you choose glucose on the x-axis and diabetes on the y-axis, this is what you see, a fairly nice division where most of the diabetes is elevated. But notice on the far left up here in the pink or red zone, there's some people here with blood sugars of 70. Are these really diabetic or not? This needs to be looked at. This is a 26-year-old, weight 150 pounds, BMI 21. So it's really hard. They may be mislabeled. There's where you go back to square one, look at your database, and maybe there were errors made. By the same token, if you look at the blue down here and you look down on the x-axis, there's a blood sugar of 270, one here about 365. Certainly may be errors. And then what I already showed you, here's the distribution of cholesterol with several high and one low. And then you introduce the outlier widget, which looks for distances, and you can adjust if you think you have about 7% outliers, you can use that. And the neighbors, it's really looking how far away are the closest ones, and you manipulate that. And then, for instance, let's increase it to 25, and you look down, and again, it basically got rid of 24 outliers. Let's go the other direction. Let's go down to 10. And it still is excluding 23 outliers. So basically, that's what we want you to know about outliers. They're common. You should visualize them. You can calculate them mathematically, if you will. And then you need to probably do a chart review to find out more whether they're real or not. And if you want to exclude them, you can delete them. You can also run your model with and without them using the outlier widget. Thank you. Part 2 will be binning by David Petrishkoff.
Hi, everybody. I'm going to go over part 2 of today's session, which is how we bin data. Now, what is binning data? Binning data is taking data and trying to put it into logical categories or put it into categories that the algorithm appears to like the best. And what does that mean? Well, let's say, for example, if I have a large data set about patient age, and I want to break it out into certain different categories like 10 to 20, 20 to 30, 30 to 40 years old, and so on and so forth, with a delta of 10 years old. And that's a very common thing. Now, that might seem logical, but that might not be the most correct way to break out the data into different bins. Like if I have very little data on the low end of the ages, a lot of data in the middle, and then very little, around the 80, 90, and 100-year-old people, then breaking it out into delta 10s is really not the best idea. So what I'm going to do is walk you through the different options that we have in Orange for doing this type of binning. Oh, by the way, Orange calls it discretize, and it has a variety of different tools for that could help us with that effort. One of them is the mosaic plot. The other one is the pre-processing plot. And then we also have a special widget, the discretize widget. And again, what are these widgets? They're little round computational, usually orange or other colored types of circles that show up on the canvas, and they do computational things for us. And then we connect one with the other if we want to do other certain types of passing information on from one to the other. So again, what's the goal of binning? I mentioned twofold. We want to, first of all, when we're breaking out data and trying to explain it, trying to do some exploratory data analysis or exploratory data visualization and explanation to viewers of the data, we want to be able to describe to them what's actually going on. So we have some pros of binning and we have some cons of binning. And if we have numerical data, it's very nice to break it out in bins. And we have a few different options that I'll show you in a minute of what Orange can do, different types of binning, different binning options. And but we're going to stick with one of the more simpler ones of those options as I demonstrate that for you. So again, what are the advantages of binning? Well, I have three different methods of how to bin, and I'll show you what they are in a minute. But it's grouping our data into different groups, and sometimes it's a little bit easier to explain. But that comes with a disadvantage, which is what we call the con of binning. And the con of binning is going to be, it's kind of like it's referred to as a subtractive type of visualization. And what does that mean, subtractive? We're actually taking away some of the raw data when we're actually doing binning, because we're forcing it into a certain group, like I said, either 10 to 20, 20 to 30-year-olds, 30 to 40-year-olds. We're taking away from the algorithm or the analysis the individual raw data. So that's one of the cons of binning. So again, the advantages of binning, we have to watch out when we use it and when we don't use it. It's advantageous very often when we're trying to do data visualizations and data explanations to a variety of people that are looking very interested in finding out what we did with our analysis. But when we're talking directly and feeding data to the algorithms might not want to have that kind of split. They want to have the raw data themselves. So we got to watch out that there's two purposes for the binning. One, just so humans can understand it. And then as far as the algorithm is concerned, the algorithm really doesn't care, with one exception. Let's say, for example, we have a diabetes data set and we already have it pre-diagnosed, where a doctor has said, these patients are diagnosed officially with diabetes and these patients are officially not diagnosed with diabetes. So that's what we call a classification problem. So it's binning that data into they have a disease or they don't have a disease. Now, another very interesting thing is that if we didn't have the binning for the diagnosis, we would have the values behind it. There was a very specific value. And sometimes these values change over time. Sometimes, in years past, what was considered a high or low cholesterol, those opinions have changed over time. So sometimes it's more important to show the absolute raw values and not the current diagnosis, which could possibly change over time if doctors and medical experts in the future and researchers said, no, actually a person with diagnosis is that we diagnose with diabetes or some other disease is actually above a different certain value than what we picked in the past. So much for that. So let's have a look at this figure right here, figure 211. And this shows the different types of discretization or binning that's available in orange. And we can see we got 4 different options here. We have what's called an entropy NDL discretization, which you could read about a little bit, is good for, when the Y is a classification. And then we have what's called equal frequency binning. What does that mean? It's gonna not take, like I give you the example of, the delta 10 of ages, which is not gonna do that. It's gonna say, you know what? I have, let's say I have, 100 data points, and I'm gonna break them out into 4 bins. So each of those bins gets 25 patients, and whatever that is, 10 years old to 22.5, and then from 22.5 all the way up to 43.75. And then after that, it can take some other type of very unusual data split. And the reason it's doing that is because we would check this option where we're saying we want to have equal frequency of patients in each one of the bins. And then I could force it, you could see option 3, equal with bins. And that's pretty much the same thing as it was saying originally. If I say, all right, I really want to have 10 to 20-year-olds, 30, the 20 to 30, 30 to 40, and so on and so forth. Or I pick option number 4, which is, remove numeric features. So those are the different options I have in the pre-process widget, 4 different options. If I go down to the discretize widget, I got a few more different options that are available for me. I have some of them that are available on top. And here we can see that, leave numeric, and we have equal width, we have equal frequency. And I have a few other different options here at the bottom where I could click each one of the columns separately and say which option I want to use. So I could have different options for different columns of data I have in my data set by picking any one of these 14 different options that are here. And then those 14 different options are described as you see here. And so again, if we want to come back and say, all right, now if we want to come back and look at just an OWS file, what is an OWS file? It's a collection of these widgets, which you're seeing right here, that I'm showing here in figure number 2.13. And I'm going to go to the live orange OWS file, which actually shows these active and not just a screen copy of it. So this shows you how you would set up the data in the widgets to give you all possible options for how you might want to not only bin the data, but also visualize the bins. And this is the beauty of Orange. Like in normal software or in a normal coding, you got to remember, okay, I got to do this and that for the mosaic plots. I got to do this and that for, the scatter plot, and I got to do this and that for the distributions. I got to do this and that for the ranks. No, if we have an Orange here, we've already laid out this entire workflow of everything you might need that's ancillary to the world of binning, and we have it in one workflow, and you just have to click on it and tell it what you want to show. So at this point, what I'm going to do is I'm going to hop over to the Orange workflow, and this is now an active workflow. This was screen copied like I showed you there, and here we see, when we send you, by the way, an OWS file, it doesn't have the data in it. It just has all the commands, all of these widget commands. So when you get this and you double click on the file, you would normally see mine is already loaded with data. You can see I have data here. Yours, you're going to have to then click on this folder button over here and upload which data is you want to upload and do the binning with before it'll be available. So it's just a particular situation with Orange to keep the file data sets down so it'll leave the data set out. So we would typically, for this whole class, we'll send you these OWS files, which we call workflows, if they have a combination of workflows of what we're going to do with these widgets. And then we'll send you the data files separately. And then you have to then go at the far left, which says File, double click on it. You double click on this folder button, and then you tell it where in your computer that data file is, and you say Open, and then that loads that workflow. Okay, so what's going on here? So once you load the workflow, let's have a look at the file widget off in the far left. Now, off in the far left, Orange has already made an intelligent guess. It says, all right, let's see, Dave here, you gave me a bunch of numerical values, you gave me some categorical, and oh, by the way, you gave me a diabetes categorical value that I am assuming is the target. So it's making an attempt, a smart attempt at saying the target is diabetes 1 or 0. And what does 1 or 0 mean? It means yes or no. And if, for example, if Orange had selected the wrong target, you just have to click on where it says target and then say either skip or change what you wanted to do if you wanted to make something else the target. But that is correct. I want it to be the target, so I'm going to leave that like it already did. So it's guess it already made. And you can see I already have the mosaic plot is already connected to it over here. And there's other options over here. Now let's first of all have a look at the rank widget. Now you might say, why is the rank widget attached if I'm doing binning? Well, you might want to know what are the most important factors. See, what Orange has already done is done, so to say, a multiple regression analysis now of the data. And it's already determined with 3 of the possible 7 scoring items. It says, you know, glucose is the factor that actually correlates the highest with somebody being diagnosed with diabetes, followed by age, but you can see glucose is much higher as far as a value of variable importance, and then come stochastic blood pressure, and then come a bunch of other factors. And these are just 3 of the 7 different ranking factors that are chosen. If I select all of them, and it'll show all of the different ranking factors, and then you can compare which ones are ranking what. And each of these ranking factors have a different specialty for how they're ranking. For right now, let's look at the information gain. And the information gain is telling us glucose, age, and systolic blood pressure. So I want to remember that, because when I'm doing binning, I'm going to want to look at those first. All right, so now I know what that looks like, the rank. So I'm going to go back here to mosaic plots. I'm going to double click on it. And automatically, the mosaic plot, I don't have to tell it, break it out into 4 different bins. It's already made that decision. It's saying, you know what, you could change it if you want to with a different widget, but right now for the mosaic widget, I'm going to break it out into 4 different widths. And I told it that I want to, it automatically puts it into equal frequency bins. And how do I know that they're actually in equal frequency bins? Well, what's interesting about the mosaic plot is each one of these slices of bread, so to say, that are standing on its end, each of them is, its width is depending on how much data is in there. And we can see right here, the instances, there's 97 data points in the one where that systolic blood pressure here is less than 121.5. The bread slice, so to say, to the right of that, there's 104. So it's picking very, very close. So again, it was 97, 104, and the one to the right of that is 96 patients are in that one. The one to the right of that, 93. And it's automatically painting the color, 1 for a diagnosis of diabetes, red for that, which is 1, and blue or 0, which means no diabetes. And so how do we interpret this chart? And, you know, like I tell all my analysis students, you know, you get 1 point for making the chart, and you get 99 points more for interpreting it correctly. What we see here is that for higher levels of systolic blood pressure, we do see a higher tendency of diabetes actually being diagnosed for those patients. And again, these were not in equal bins with, we could see, all right, this slice over here is systolic blood pressure less than 121.5. The one to the right is 121.5 to 136.5. The next one is 136.5 to 148, and then above 148.5. When you can see that we have increased levels of diabetes diagnosis. So that's the advantage of a mosaic plot. Now, if I say, you know what, I don't want to use the defaults of the mosaic plot. It actually just showing me, 4 slices of bread, 4 widths of equal frequency. I want to pick my own equal frequency number of slices of bread, so to say, on the mosaic plot. So to do that, you would add the select columns widget. And what is the select columns widget? It's going to tell you, okay, it'll give you the option of all your factors. You could corral them into the predictor section, like you could see I already have done over here. The target value, which is diabetes, yes or no. And then we have a meta factor at the bottom, which is really just a categorical factor for gender. So, and then that widget is connected to the discretize or the binning different option. And here we could see what I have already preset. There's a lot of different options here. I could put, natural binning, desired bins, but what I picked here is equal frequency intervals. And if you remember, the original mosaic on its default had 4 bins. But here I said, no, I want to have 6. I can change it whatever I want to, but I said, I want to have 6. And then I just click on the mosaic plot that comes after that that's connected to the binning widget. And I double click on that, and we could see now that it has 6 equal frequency bins. And it has the same different type of situation where they have equal frequencies, and I could hover over that and see exactly what's going on. And I could see that there's 63 as opposed to 97 like it was before. And oh, by the way, everything in this section is his systolic blood pressure of 117. And if I move to the right and I click over it, I could see exactly how many instances and exactly what the bin with cutoff points are. But again, here I have the same conclusion that I had before. The higher the systolic blood pressure, the higher the tendency of those patients to be diagnosed with diabetes. And you might say, okay, no, all right, systolic blood pressure, all right, that was the 3rd on the list. That wasn't the highest correlator. Where's the highest correlator? Well, I could click on this arrow and say, show me my command strings, or just show me the graphic itself. And I go over here and I say, all right, I want to have, glucose, since that was the highest correlator, and see what that looks like. So here we see in the mosaic plot, we see quite a bit of jump that for different levels of glucose, first of all, I don't have not much is happening, and I start to get a little pickup, then all of a sudden I get a really big pickup after the glucose is, above 99.5, between 99.5 and 120.5. And then after it jumps to 120.5 or greater, I get a much higher level of patients that are diagnosed with diabetes. And I could do that for any one of the factors that I have. And here I could see with age, here I could say that, I have age, and again, it's equal frequency, which is kind of nice. And here I could say that, for the age group 54.5 to 64.5, which is, 9 years of age, that that age group has the highest proportion of diabetes diagnoses. And when you get above the 64.5-year-olds, it drops down a little bit. And we could interpret that way because the mosaic plot has made sure that we have the same number of patients in each one of these horizontal slices. See, I got 62 here. I got to the left of that, I have 66. Then they got 67, 66, 64, and 65. And how I know all that? By hovering over that slice of bread, so to say, that's standing on its end as the mosaic plot. Now I could add more. I could add more columns to a. We put glucose again as the start, and we know that age was the second. I could pick, for example, age as the second, and I get, a little bit more of a complicated mosaic plot. And I could pick 3 and 4 different factors. Then it gets to the point where it becomes hard for you to understand, and then maybe even harder for you to explain to others. And you can see here, then I have a double cutoff here. Here I have the age explanations over here, and then I have the glucose explanations over here. But I don't want to get into that complicated type of explanation right now of a mosaic plot. Let's just leave it showing one of the factors at the moment. But as you see, there's other things that are going on in this workflow. We also have a scatter plot. So I could do a scatter plot. You might say to yourself, wait a minute, are scatter plots just for continuous data? Well, I could do a scatter plot with binned data. And let's have a close-up picture of what's going on here. And what exactly is it doing? Well, let's have a look at the horizontal axis, the x-axis over here. It's saying glucose levels. It has all the bins. And the lowest level of glucose is off to the far left, and the highest one are to the far right. And again, it's trying to keep roughly equal frequency bins when it could pull that off, because it's also dealing here with the scatter plot with age as the y-axis. So it's got higher level of age as I move up on the y-axis, and higher level of glucose to the far right. So how would we interpret this graphic over here? Well, we could right away see that obviously we know from the rank widget that glucose is the highest correlator for diabetes. And so it's no surprise to us that the higher the glucose, we see more of the red dots. And oh, by the way, what are the red dots? Same as we saw in the mosaic plot, the red dots in the red shaded area that it's showing us. It's saying, hey, this red shaded area, these are where most of your people are that are diagnosed with diabetes. And the blue means those are people that are not diagnosed with diabetes. So you can see the blue regions are more off to the left. Okay, now what about the age factor? So in other words, I have to the far right, I have high glucose. And then the more I go vertical on the graphic, higher up in the y-axis, I have people with higher age. So generally, I could say that on the far right corner are people with very high glucose levels, and then with higher age levels. And in general, that's where I find most of the patients that are diagnosed with diabetes. With, oh, by the way, one exception down over here, this red dot, and one exception over here. But in general, we could see, and there's a few exceptions over here too, but in general, we could see where that data is lying. So that's how we would interpret the scatter plot. And oh, by the way, on the scatter plot that I showed you, I could go in there with this right arrow and say, you know what, I don't want to have age as my vertical axis. I want to have systolic, let's say I want to do systolic blood pressure, and I could have a look at what that looks like. So I could select whatever I want. But that's the advantage of if you first do add the rank widget, you know which factors are the ones that correlate the most, and then you could fine tune your visualization of that graphic to match, whatever you're looking at and whatever is of interest for you, like the highest and the second highest value here. So let's move on. So I showed you how to do mosaic plot one time with the default 4 groups, and then with the mosaic that I could change. I showed you how to do that in a scatter plot. Now I have also distribution plot. Let's look at the distribution plot. Now, the distribution plot, what is it doing? It's breaking out also. We could see here right now it's systolic blood pressure. We could see it's breaking them out. It's kind of like a histogram for, again, all the frequencies which are blue are those which don't have diabetes. And again, we could see the red gets higher when we have higher systolic blood pressure. So it's showing the blue and the red next to each other. Now, if I say, wait a minute, systolic blood pressure was only the third highest, let's have a look at the glucose. So I want to go back in here and just look at the glucose. I could do that and select that, and we could see. And if I say I just want to look at the graphic and not the options, and again we see this dwell point where not much is happening until I start to hit a critical glucose level, and then all of a sudden I'm starting to see a very steep rise in these red bars, which are the diagnosed groups of patients with diabetes. And I could do that for any of the values that are of interest for me. And I could, I typically would want to stick with the ones that correlate the highest, but I could also explore what the other ones are doing. Like, for example, body mass index, I could also see that it rises up and it also drops. But again, keep in mind that BMI was not exactly the highest correlator. And so if I want to get out of this distribution, and if I wanted to, for example, I said, in the discretize, I could see over here, I told it I want to have 6 different bins, equal frequency bins for each of these continuous variable factors. And I could see exactly the cut points. But you know what? I want to look at those cut points. I want to have them in a document somewhere. Well, you could see here attached to the discretize widget is the data table widget. And when I double click on that and expand it, you could see it's kind of like you say you want to look at it in a spreadsheet format. It's showing you exactly all the different binning groups that were chosen for each of the patients here. And it's showing you all the different groups and how they were binned. And, each row is a patient, and it's showing you which bin they landed in for each of those values that were in the data set. So that is a rough overview of binning. And so that describes it. And we have the pros and cons I talked about, and we have some nice data visualizations. And again, keep in mind that whenever you make a data visualization, make sure that you also are capable of understanding it yourself and writing an interpretation comment of that graphic so for others, so that you could explain it to others. So that's all I have for you today. And so I hope you enjoyed that and understand now how to do some binning in Orange.